Welcome to the 50th lecture. We are going to start power factor. In this class, power factor is not a new term, rather, it comes from the formula of average power that we have been studying for the last few lectures. We have studied, it's a small recap of what we have been studying in last few lectures. Power P is represented as half Vm times Im times cosecant of angle between the voltage and current and is measured in watts. Or in last one or two lectures, we have also described the same power P in terms of RMS quantities, whereas these are peak quantities. And I have mentioned in one of my previous lectures, the difference between the RMS and peak quantity is that for a sinusoidal signal, this is the peak, positive or negative, and for sinusoidal signals, we have derived its RMS to be 0.707 times peak or V peak. V peak. This is V peak. So RMS is 0.707 times V peak. In terms of RMS quantities, the same power can be represented without this 1 over half. And we have proved that too in one of our previous lectures. Today we'll define a new term if we divide this product V RMS times RMS uh, by P by taking this product on the other side of the equation, we are left with this cosecant terms on the left and everything else on the right. Right. Now we define this term cosecant of angle between voltage and current as power factor. Let's give it another name, power factor. Oh, I don't need to write it again. It's written here, power factor, PF. Power factor is P over PRMS times IRMS. This one, this term is the power factor. To find out the power factor of a load or a source, we must know the power, the RMS value of voltage, and the RMS value of current. And power factor is always between 0 and 1. Value of power factor is always between 0 and 1 because we know that it's a cosecant term, and cosecant term can range from -1 to 1, right? But the term power factor, it ranges from 0 to 1, but it can be leading or lagging. I'll explain the term leading or lagging shortly. Right, it's a resistor. Through this resistor, suppose we have this current I at an angle of theta I, and the voltage across it is V or Im, or this is Vm or RMS, can be any quantity. But the important thing is that through this resistor, the current flowing through resistor and the voltage across this resistor, they have the same angle, theta V. We have proved that, and we have experimented with this fact a number of times in our previous lectures, and we have studied that for resistors only, the difference between theta V and theta I is 0. They are always the same, but only in case of resistors, and the answer is a 1. So therefore, for resistors, For pure resistors, power factor is always 1. For an inductive load, which can be a pure inductor or it can be a resistor in series with an inductor. In any case, if either it is a combination of a resistor and inductor or it is a pure inductor, in both cases, I, the current flowing through it, lags V. This means that if this is the waveform for V, the waveform for I, let's try it with a different color, maybe with this yellow. Oh, everything turns yellow. Everything turns. I think I have no other option except choosing the same color. Okay, so this is the term. This is the current for. This is the waveform for the current I. If this is the waveform for voltage V, this means current is lagging. Current starts after some time. If it is an inductor or a combination of a resistor and an inductor. For inductive loads in general, this combination of resistor and inductor, we call it inductive loads. So inductive loads, it's always the case that current lags voltage. So it has a lagging power factor between 0 and 1. The value is between 0 and 1, but it is lagging. For capacitive load, it is opposite. V lags I. If this is the waveform for current, the waveform for this one for voltage, this is the waveform for current, this one. So if this is the waveform for voltage, this waveform is for current. So current leads or voltage lags. So for capacitive loads, if either it is a pure capacitor or a combination of a resistor and a capacitor, this combination is generally called a capacitive load. So for capacitive loads, we have these leading power factors, but the value remains between 0 and 1. Right, let's move on to the next slide where we are going to solve an example. And this is a very interesting example. And that is, we are driving a load here. The load is drawing 88 kilowatt power, active power in kilowatts. Kilowatts means 10 to the kilo means 10 to the 3, and it has a power factor 0.707 lagging. If it has a lagging power factor, this means it's an inductive load. It is a combination of an inductor and resistor. So this load is inductive load. For inductive loads, we have lagging power factor we studied in last slide. The voltage across this load is 480 volts, and this voltage is RMS. This is RMS value, 480 volts. This is the line that takes voltage Vs to this load, and the line has a very small resistance, 0.08 ohms, but there is a voltage drop across it, which is not mentioned. We are given only the voltage drop across this load. This may be a motor or any other load, but it is inductive, drawing 88 kilowatt power. 88 kilowatt power is absorbed in it and has a 0.707 lagging power factor. Lagging power factor means, I have also written it here, it's an inductive load. We are required to find out the power supplied by the source. There is only one source in the circuit, this source. We know that power absorbed in the load plus the power absorbed here in this load and the power absorbed in the line resistance. If we add these two power values, this is equal to the power supplied by this source. We know that the power supplied in a circuit is the same as power absorbed. So we have two circuits where power is being absorbed, this load, motor, or anything else, and this 0.08 ohm resistor. So the power here is given. So if you want to find out the power supplied by the source, we just have to compute the power that is absorbed in this resistor. In order to find that power, we'll first find the current flowing through it. If we know the current flowing through it, we will square it, I squared. We know from the last lecture that the power absorbed in a resistor we studied in last lecture, it's I squared times R, or V squared over R. So if we somehow know the current flowing through this resistor, we can straight away calculate the power absorbed in it. How would we calculate current? We are given this power, the voltage drop across it, and power factor. Let's write the expression for the power of load. Here I have written it for you. Power absorbed in load is the voltage drop across it, the current through it times the cos of times cosecant of theta v minus theta. And we know that cosecant of theta v minus theta is power factor. So we are given this quantity 0.707, this quantity 480 volts RMS, and this quantity 88 kilowatt. So this is the only unknown quantity in this equation. We can move on to find the value of IRMS. PL is given 88 kilowatt, VRMS is given 480 volts, power factor is given 0.707. So it comes out to be 259.3 amperes. We can find power absorbed in 0.08 ohm resistor by using the formula that we studied in last lecture, IRMS squared times R. IRMS squared times R. I haven't calculated it. You are encouraged to use a calculator to calculate the exact value. And once we put that value here and in kilowatt, compute it in kilowatt, right? Whatever you get here divided by 1000 would be the power in kilowatt. And if we add it, we reach to a value where PL is not PL. I'm sorry, this is not PL, this is PS. The power, this is the power supplied by the source. The power supplied by the source is the power absorbed in 0.08 ohm resistor and the power absorbed in the load. So this is PS, right? We will keep on studying more about power factors in our upcoming lectures. Thank you.